What I'm going to talk about today is give you a brief introduction to what we're going to be using, the methodology we're going to be using. And like I said, it's called Innovative Conceptual Engineering Design. We first began this in 2008 with 3 of the 4 professors, and Jeanette's going to be here in a little bit. Let's just go over where we are. If everyone can see this, we had a great first day, great reception, great afternoon, and Jeff Hoffman gave us a great introduction to radiation. And he covered a little bit of the basics of it, which was great, and he also looked at a very unique idea for solving the problem, which some people are looking at, and which is superconducting magnets creating that magnetic field, deflecting that galactic cosmic radiation. And he showed us some of the problems, and he also showed us some techniques for how we analyzed it. And one of the things you heard him say was that, sometimes you have to do real rigorous analysis. Like you needed to know the effectiveness of those field lines in shielding the structure. And so they had to dig down in and do some rigorous high-level analyses in order to model that. But then some of the other terms that they used were well, they weren't as rigorous, what he called back of the envelope. Going to talk about the methodology. I'm going to use an example that I've used before, which tries to give a demonstration in a story form, an example form, of each of the different principles and themes that we try to utilize in this methodology. And that's the return to flight exercise. And then Mr. Larry Toops is going to talk about Mars architectures. What has NASA been looking at to study this problem? Giving you the picture from the 100,000-foot level, and how NASA would typically attack these problems, how we're working on trying to solve these problems. And then we're going to have Dr. Larry Bell talk about minimum functional habitat design. And this is going to give you a different approach to looking at the problem. Instead of saying, hey, I want 6 of my best friends to come fly to Mars with me and we want to have this much room, what's the minimum that we actually need? What do we absolutely, bare minimums, like, and go back and look at some of the expeditions we've had on the planet Earth, and you're going to realize that people had to scale back a lot and had to endure and suffer in order to make these discoveries. Okay, then Ali will talk to us about engineering, especially systems engineering. You heard Dr. DeVeck talk a little bit about engineering systems. Okay, and then after that, we will begin with some of our other speakers. Dr. Frank Cucinato will be here. So that's a recap of where we were, where we're going today. I'm going to talk a little bit about how I was trained to be an engineer by my mentor at NASA Langley. Dr. Jim Starnes passed away, but he was very much experienced, excellent in the field of structural mechanics, especially buckling. First, what's the difference between a scientist and an engineer? As we're looking to teach high school students engineering, and a lot of high school teachers come from a science background and are very comfortable teaching science, it's good to relate to the students the difference between science and engineering, what do engineers do, and how much overlap there is and how much they work together. And so this is a great quote by Theodore von Karman, the father of aeronautics. Scientists study the world as it is, and engineers create the world that never has been. Go ahead, Dimitri. Yeah, you would think it's from an engineer's perspective. I don't know if Theodore von Karman was a scientist or an engineer, Ali. What do you think? But it sounds pretty good from where I'm sitting as an engineer, because especially as someone that likes to be in the design world, the more creative world, because we have these great equations, we study these laws that scientists, by observing nature, develop. And I want to make one caveat, is that every law we have only applies to a certain limited region. Okay, we're constantly learning new things, and those laws have to be changed. And so these theories are not hard and fast, and so you should think about that whenever you hear someone and they act like this is the absolute truth. okay? It's only until we learn more and that changes. But what engineers do is they try to take those laws and create models and methods in order to be able to build things and to test things and to be able to ensure that those things do not fail. And so what Jim Starnes would do is he would take me in his office when I was an intern, when I was at Brooklyn Polytech, and he would say, okay, Charlie, now sit down, and he would draw these circles on the board. You start with a concept or an idea or a view of the world, and then what engineers do is they have to develop a mathematical model for what they see. They go in the laboratory, they conduct experiments. Those experiments don't always simulate reality. They approximate reality. And then we compare our analysis with our experiments, okay, and we find some sort of correlation. And it's in that correlation that we feel like we understand the problem. The problem is that more often than not, when we conduct the experiment, the analysis and the experiment do not agree. And so we go back and forth, hence the double-ended arrow, trying to relate our analytical understanding, our mathematical model of the problem to what we're seeing in the laboratory. Sometimes the errors are in the experiment. We're not simulating reality like we think we are. The boundary conditions, there are no really fixed boundary conditions in structural mechanics. Or sometimes it's in the analysis. But we keep doing this dance. Once we understand the problem and we have really good correlation. Oh, and the other very important thing that Jim Starnes would say is in the experiment, you test things to failure. And you do that for a couple of really good reasons. You've really arrived and you really understand the problem if you can predict when it's going to fail. Okay? If anyone tells you, yeah, the stress is this, okay, tell me when it's going to fail. Can you predict that? Okay, so we test things to failure. And we're going to talk a little bit about that. Failure is very, very important. It's very important as a research methodology and an understanding of failure. Okay, and when we do that, and now our analysis can predict failure, we can reliably use that analysis to now do some design work. Okay, and this is the part which I think is, there's creativity in each one of these bubbles, coming up with innovative ways to solve problems and to run experiments. But I think the most creativity is expended in this design phase. Okay, and that's where you get to use your imagination, okay, your imagination to use that analytical model, and you can create whatever you could think of in your mind, okay. You go out in the laboratory, you design it, and then what you do is you go back in the wind tunnel or in the test stand and you test. And more often than not, your analysis, you've exceeded the envelope in which your analysis and your assumptions in your analysis was valid, and something's going to fail. A failure mode you didn't account for in your analytical understanding, didn't model it in your analytical modeling, occurs. That's why you do this cycle over and over again, okay? And with different levels of your concept. You start at a very small level, subcomponent level, and you build up, and you increase the level and understanding of the problem with the rigor you put in your analysis and the way you conduct your test, because you're getting closer and closer to a full-scale test. Okay, but the concept is what's key. Dr. DeVeck, my advisor, Rafi Hafka, worked a lot of their life and did a lot of research in what was called multidisciplinary optimization. I thought that was the keenest thing in the world. That's why I wanted to be a research engineer. I worked with Rafi as an intern at NASA for several months, and I said, wow, I want to be able to understand mathematical optimization, mathematical programming. But what happens is that starts with that initial concept. But how do you have that concept? And that's where humans have an advantage over machines. We use machines to do the mathematical programming, but coming up with that innovative concept, that idea, totally changes the order of magnitude of the benefit you gain from that concept. Okay? So whereas mathematical programming is an incrementally optimizes that idea, by merging ideas, by coming up with totally innovative ideas, totally opens up a whole new arena. Would you agree?
No, I agree with you totally. There are attempts to have machines be creative,
Yeah.
but it's really hard, and it's not. You look at it and you're like, that's.
Nah.
For example, seeding certain things that could grow or shrink, and basically like structural topology optimization. Where you just basically say,
Yeah.
here's your sandbox, and just put the material where it helps you the most, and the structure sort of emerges. But it's not really what you're talking about.
It's not. And I know artificial intelligence, people claim to do that, the Turing test, to say, oh, we're getting close to where machines are not creative. That's the difference between humans and machines. And, that little Michelangelo, we're not quite there. We're not quite reaching the gods, but we're approaching it, okay? And so I'm going to talk to you a little bit about a building block approach. It's what all good engineers do. It's what you saw young, what's this guy's name? Sidney. Young Sidney present yesterday. Not so young Sidney present yesterday. He did a fantastic job. He showed you the spiral approach 3 times with the level of fidelity increasing, the size of the problem increasing. These simple figures represent a concept, an idea that we had for a reusable cryogenic tank. You have cryogenic hydrogen, but we wanted to create a rocket that you could fly to space, bring the tank back, and reuse it. Never been done before. Minus 420 degrees, we said, you know what, let's use a sandwich structure, and we'll evacuate that sandwich, so we'll make it like a thermos bottle. So that structure, and this is a term you're going to hear, will be multifunctional. Okay, it will act as a really efficient structure, which honeycomb sandwich does, but we're going to evacuate it, and now it's going to be a great insulator. Okay? And so we had these subscale tests. And what I'm going to tell you to do is what Jim Starnes and other great engineers like Henry Petrosky at Duke University, wrote several books on failure, said design is really us obviating failure. So you look at your idea and all the different ways it could possibly fail. And that's something that's very difficult to do for inventors, for people that are very creative. When they create something, that's theirs. They hold on to it. They love it. It's almost like their child. They don't want to look at any imperfections. They're in denial. And they don't want to hear that their child is ugly. And we all do it. I think it's natural human tendency, especially for those who have kids. But what I'm going to tell you to do is, when you do create something, you have to be totally objective in how you evaluate that. If you look at some of the really creative people, when something's not right as you see them tossing up balls of paper, trashing the entire thing. My grandfather was a tailor from Italy. When I was a little kid, I had these great suits, but I can remember this little bald Italian man with pins in his mouth ripping the sleeves off of these jackets, and I would be frustrated. But it's that striving for perfection and that creative nature that you have to be able to do that. Okay, we could do that at very small scales. And what you're going to be teaching here, that we might not have enough time in this week, but the next time we teach this to the students, is teaching people how to do this rapid concept development. Okay, teaching them to say, I have this great idea. Now, how do we prototype it and simulate our idea in as realistic way as possible, as inexpensively as possible, as quickly as possible, so that we obviate those failures. We think of all the different ways it could fail, and we build it into a very simple test. We go out in the laboratory and we test, fail, and you're going to hear me say failing fast and furious. Dr. Jack Mattson invented the term. It's called intelligent fast failure. It's in his book. So if you ever read or hear any other papers that say intelligent fast failure and they don't defer to this man and recognize this man, they're basically stealing his idea. So what I said was, you know what? If this is going to work, you have to maintain that vacuum. If you don't maintain that vacuum, if it leaks, if you get hydrogen going into that sandwich panel, or if you get air going into that sandwich panel, it's so cold it liquefies. It liquefies, and then once you launch and the tank boils down and the sandwich gets heated, it can't vent, and that's going to blow up that sandwich panel. So you have to maintain that vacuum. And it's very easy. You could do these tests at a very small scale in a laboratory. But in a building block approach, once you pass those tests, you continue more and more rigorous in your analyses, more and more constraints till you finally test a full-scale specimen. And if you don't do that, you take the stepwise approach, increasing rigor in the analysis and experiment, and you're constantly testing to failure so you know the limits, you know if you can predict it. If you don't do that, and this was a real program, if you miss one of those key steps in that building block approach, if you didn't think of all the potential ways it could fail, okay, this is what happens. Okay, it blows apart. We knew this was going to happen. We told the people that this is a potential problem. They did not go back and test in the laboratory. They built a full-scale, multi-lobe composite hydrogen tank. Very expensive, very difficult to do for the material scientists so that it doesn't leak hydrogen, which is the smallest little molecule, right? Blew it up, and you know what happens? It causes failures to some really big, expensive programs. This was a single stage to orbit program. If we could accomplish this, it would have been phenomenal. We'd be flying these huge rockets to space, bringing them back and reusing them. It all failed, okay, because of something that was missed that could have been done by high school students in a laboratory experiment. So that's why we're learning this, and it's going to seem very simple. Okay, the first phase is going to be that problem definition phase. We're going to hear from people that are our clients that are going to ask us to produce something, and we listen to them, what their requirements are, what their needs are. But we listen to them, but we don't take it as if they absolutely know what they want, because more times than not they don't. But they're going to define the problem for us. You're going to listen to Mr. Larry Tubes, and he's going to tell you, you know, we want to get to Mars. This is what we want. And he's going to give you some requirements, what we like to accomplish, scientific requirements, human requirements, life science requirements. And then they're going to say, okay, these are the constraints. This is the problem. They're going to define it. And now we have to understand the problem. And so we're going to be listening to the experts. We're going to be listening to experts in radiation. We're going to be listening to experts in environmental control and life support system. And what I want you to do, when I use that term expert, I don't like to use that term expert. These people are very knowledgeable in this area. They're giving us an idea of what's been done before. Don't think this is the only way to do it. Don't think that what they're saying is absolutely correct. I want you to think critically. I want you to pound them with questions. And what we want the students to do is we want them to be critical thinkers. We want them to understand it and to prove it to themselves. Totally immerse yourself in the problem. This is where I want you to go. Dig into the literature. Dig into the research. You saw what Sydney did. Did a fantastic background search. Pulled up papers that I had never seen before. And many of the people that have been working that problem had never seen before. What he did was he went back in time, looked at every way other people tried to solve the problem. That's the way I like to solve the problems. Many people that preach creativity say you shouldn't do that because it biases you to these ideas. And so I'm going to caution you, when you do that, you have to understand that you're just trying to understand the problem. We're looking for other ways, in addition to ways to maybe merge several methods together. So creativity can be a combination of ideas, or it can be a totally new idea. The other important aspect is the team development. Okay, when I read about creativity, when I practice it, diversity is the most important asset. I think it's what makes this country still maintain its leadership, our tolerance for diversity. Diversity of thought, background, experiences, capabilities, the way you look at a problem. When I did my doctoral dissertation, when I was researching, I researched people that looked at this problem from different continents: Italy, Hong Kong, Russia, the United States. And I believe I had a totally unique view of this problem, where these people were solving this problem different ways. I don't think they had as good an understanding of the problem as I did when I looked at the problem. So the same way you form a team like that, I want to encourage you and your students to make sure that they treat everyone on that team with respect. Communication is very important. You listen to that person, and you understand where that person's coming from. So I like the people to give a very detailed explanation of everything they've done up to this point. So you get an understanding of where this person's expertise is, how they look at the problem, and then to listen. And there are many things you can do team dynamic-wise to make the magic happen, because I think the creativity is really a team sport. And there are very few unique lone innovators, lone creative geniuses. And so you're going to hear and watch us use creative techniques to think outside the box. Dr. Jack Mattson, Sven Bieline, and Jeanette Yen are going to be showing you how to do this. These people are not just creativity gurus. These are very accomplished people in engineering and science, okay? And so what they're telling you is they use this because it is important, and they see the benefit of doing that. And then we're going to get the teams of students and you to actually think outside the box. And you have to lighten up, and you have to throw these ideas out. There's many different ways of doing it. We'll go through a concept ideation phase after we listen to the technical experts. And you have to remember, this is a boot camp. Okay, you're just going to touch upon these subjects and get a little bit of time to practice them. And then what we want you to do, to think about when you go back and do it with the students, you'll have a week or several weeks to practice this technique with the students. And then they'll have 6 weeks where they'll basically try to come up with concepts and ideas and hopefully prototype some things. And then what we want you to do is then carry that forward and have these students work on those same ideas, continue this journey of problem immersion and constantly this continual learning throughout that process, coming up with improved ideas and going out there and testing those ideas. Teach a little bit different ways of how do you evaluate these ideas. And this is a critical part, and this is how do you do the concept analysis and development. Concept development, rapid prototyping, rapid concept development. You go through that analysis, design, prototype, and test phase, like Jim Starnes said, those 3 bubbles, in a very efficient way, and hopefully through multiple cycles. And what the idea is to rapidly mature these ideas as quickly as possible so that you can say, you know what, when NASA needs them, when Lockheed needs them, when someone else needs them, they'll be ready. This is good enough, and we've taken it to a rigorous enough evaluation that we could say, you know what, we can invest some money in this, and it will probably be successful. Remember that 1% of expenditure, right, and locking in 70% life cycle cost. We want to make sure that we maybe use 10% in the concept development phase, but once we lock in on that, it's going to be very successful, and it's going to be very efficient. And that's the whole process. And let me tell you, that makes or breaks companies. NASA is struggling with this right now and trying to reinvent itself and remember how it did things like that in the Apollo era. And it's something that was built into the way we did business when we were taught how to do this as research engineers and how the Apollo engineers developed those amazing things. One of the movies you're going to see that Ollie brought is From Earth to the Moon, and it's about the creation of the Lunar Excursion Module. Unbelievable feat of engineering magic that they were able to do, and with a small team, and it's just phenomenal. So the major themes that you... Go ahead.
Charlie, can I just give another example of, and this has been written up quite nicely, we could share that, the Pathfinder. I think we talked a little bit, the Mars Pathfinder, if you remember, that was in '97, that little rover Sojourner and the Pathfinder, and the whole idea of landing on airbags. Right?
That's right.
I think Sidney mentioned it in his talk.
That's right.
And at the time, that was heresy, right? You had to land with retro rockets. And a lot of the early stuff that team, that was a fairly small team, not funded at a very high level. They just started playing around with airbags and bouncing them off, buildings and just dropping things and just, I think the Pathfinder, and then it was hailed as a great success, of course, but I think the Mars Pathfinder went through a very similar process than what you're describing here. It was a real breakthrough.
That's right. And you're absolutely right. I don't want you to think that all of NASA operates like that, or has these problems. Human spaceflight has had these problems. There are pockets of divisions, branches within NASA organizations at different NASA centers that are doing very, very creative work. And JPL, Jet Propulsion Lab, is one of them. And because they have this culture, they're still able to maintain that culture. Let me say that the Human Spaceflight Program and Johnson Space Flight Center started with 50 research engineers from NASA Langley. So they had that culture. They had that seed that developed that culture, and what happened is that culture evolved and that culture changed. We built these rockets. We became arrogant. We thought we were the only people that knew how to get humans into space. You might hear that now, and you might read that in the newspapers when you see these commercial companies putting people in space, and people are saying, well, you know, that's going to fail because they didn't do this, or they haven't used these criteria. But, you know, the people that did this for the very first time, no one had ever done it before. And so, but now we've become arrogant. We think we know it. We think we understand it. We think shuttle is an operable vehicle. What happened? Right? We thought it was because, and we'll talk about that. You have a string of successes. It only feeds that arrogance, okay? And it leads to failure, okay? Because we're never constantly testing what we know, what we don't know. When we see something that wasn't correct, we should try to understand why that anomaly happened. When you talk about the Challenger accident and the Columbia accidents, what Diane Vaughan, the sociologist, wrote about was, and the term she used was normalization of deviance. We see deviant behavior, but we don't see any bad outcome. We tend to normalize it. It's normal. Don't expect anything bad. Instead of saying that foam is coming off, why is it coming off? It's not supposed to come off. What will happen if it hits this part of the vehicle at this velocity, if it hits that part of the vehicle at another velocity? Never be content that you think you know the answer to the problem. And so that's why we have some of these themes. One of them, we developed these themes. There are 7 of them. If you have any suggestions, we're open. We will add more to the themes that we teach in this course. The first one is the human mind, use it. There is no substitute for the human mind and as the prime source of creativity and innovation. I truly believe this. I think that's what makes humans unique. And tools are there to enhance our efficiency, but they're not an aid to really the creativity. And so we have to know when to use computers and when do we use humans and use them together. And so when we teach our students, if something doesn't look right, if it doesn't pass what I call the look right test, that's a warning sign. That's a red flag. We need to dig in and understand it. Prove it to ourselves. Go out, do a back of the envelope calculation. You heard Dr. Hoffman yesterday talk about these back of the envelope calculations. We have these great computers. They give us an answer. And especially for the younger students, we tend to believe that that's the truth. Do a back of the envelope, okay? If you're a structural mechanics person, you do your beam theory, and you say, are we in the ballpark? And is this close to being correct? Never trust your first instinct to trust the computer. Okay, arrogance. We talked about this a little bit. When people ask me what was the cause of the shuttle and the Columbia accidents, I believe it could be said in one word: arrogance. People there thought they knew the answer to the problem. They thought they knew why those O-rings, why that seal was opening up, why those O-rings weren't functioning properly, and they relied on test data that was telling them that there was a problem, but they looked at it and made themselves think that they were okay. Their tests were not representative of the real problem, okay? So they were incorrect tests. They thought it could be a potential failure mechanism, but the tests they ran were not representative of the real true physics of the problem, and we'll talk about that a little bit. And so I know a lot of arrogant people. I know a lot of brilliant people that aren't arrogant, and I always tend to go with those folks. And so take what they say with a grain of salt, and always question. Understand the mechanisms of failure. This is the thing that Jim Starnes drilled into us. Understand what is causing this failure in his quest for understanding buckling and nonlinear structural behavior. Test, test, test. He did analysis. This is, of course, the Comas-Narrows Bridge for really old engineers like myself. This was the symbol for a real catastrophic failure when someone did not address all the potential failure mechanisms. Henry Petrosky talks about bridges and why they fail, and you keep extending your knowledge and making the spans of bridges longer and longer, and all of a sudden they become so flexible that they're interacting with with the airflow over the bridge, and that flexibility is causing the bridge to flutter and fail catastrophically, a nonlinear dynamic instability. And so they missed the failure mechanism. They kept extending the span of the bridge using conventional methods, not introducing. They never went back and said, are we at the point where the bridge is so flexible that now it's going to interact with the airstream, it's going to deflect, and that deflect is going to cause a dynamic instability. The oscillations are going to get worse and worse, and it's going to self-destruct. Okay? So that's in that cycle of things. What happens is we get comfortable with that analysis. It also talks a little bit about how strings of successes can make you feel secure in your understanding of the problem. You may become a little bit arrogant, and you forget to question when you start seeing things. Okay? So studying the history of past failures is very important. And like Dr. Petrosky says, obviating failure is is important for successful design. We're going to teach failure is not an option, it's a requirement. We want kids to fail. We want to fail. I'm going to show you an example in the next half of this pitch where we went in my friend's garage and we failed like crazy. And as long as there's good failures and bad failures. And there's failures that are very necessary, exploratory failures when you're a researcher. And then there's other failures which are probably blameworthy failures, which you probably missed a step, you didn't follow procedures, and it causes an accident. Okay, and so there are ways to fail. And we want to teach you how to fail in the laboratory and how to learn from those failures, because that's where you gain an understanding of the problem. That's where you'll never forget that problem. And like I said, strings of successes lead to failure. Going to talk a little bit about panning out and zooming in. And when Sidney talks about his functional decomposition, I want to give you the big picture from the 100,000 foot level. Panning out, a good systems engineer, engineering systems person will look at the entire magnitude of the problem. Okay? And then we're going to take you down into your part of that problem. So you're going to learn about Mars, learn a little bit about going to Mars, learn a little bit about the environment of Mars, and then we're going to quickly focus in on our aspect of the problem. Okay? And it might be radiation, or it might be environmental control and life support system. And you're zooming in. And the reason why you're zooming in is you have to go into excruciating detail in order to understand some of these failures and where these failures happen. And so the level of rigor that you do at that component level has to be excruciatingly high, an excruciatingly high level of detail. But then when you make changes at that level, you have to step back out, pan out, and see how it affects the other levels of your problem. Okay, and what Dr. DeVec has worked on in his past is multi-level optimization. You look at optimizing at the systems level, at the very large level, zooming out, and then optimizing individual components. But then you also have to transfer those changes to the other levels. When you make that change at the component level, how does it affect the big system? So you keep the big system in the front of the back of your mind. Okay. Very important to recognize that you need to allow times for these ideas to change, to morph, to gel, and to commingle and to cross-pollinate. Okay, sometimes you need to recognize when your team needs to just take a break, go to a museum. I call it taking a cognitive road trip. Take a vacation. Look at other things. But what I like to do is you immerse the people in the problem, okay, so that you're constantly thinking of the problem, everything you're doing. You know, it's the problem that's the hook that gets you into, you know, this is exciting. How do you solve this problem? And so you'll hear a lot about gee, creative people, and you look at all their, Mihaly Csikszentmihalyi in his paper interviewed thousands of people, and he had these qualities. One of the qualities of a creative person is that persistence, that perseverance. It's like, why can't I solve this problem? Those are the kids I want to work with. Why can't I solve this problem? But as you're immersed in the problem and you're thinking about it, you're walking around, you're looking out the window, you're observing nature, and that's when those aha moments happen, okay? And you'll see this, and I've experienced this, that teams of people, they come together for 1 week, they have 20 to 60 ideas. I'll let you go home for a week, and if you're communicating virtually, if you're communicating with your friends, the size of that creative pool of ideas starts to grow, and it's natural, and that's a good thing. We have to allow that to happen. The other thing is, some people think that they're not creative, and I'm here to tell you, everyone is creative. We were creative, we created, we are creative. This is one of my heroes who espouses all the elements of a creative person and engineer. He was not only the consummate artist and sculptor, but he was a phenomenal creative engineering genius. And of course, the idea that it's a team aspect. One of the things we'd love to be able to do is to identify where the idea comes from and how that idea changes over time, how that idea evolves. If we can capture that, if you write in your idea journals, if we develop a virtual platform where people could chronicle their ideas and you could watch how it bounces off the individual people on the teams around the world, you watch how that idea changes, and you could see the whole chronology of how that happens, and I think that's worthwhile to do. And so those are the 7 themes. Are there any questions? I know it's early in the morning. Larry.
I'd like to just maybe add something if I might. This is something I've given some thought to. I want to go back to what you said about
Oh, did you hit the mic? Did you hit the mic?
I did. Is this better?
Yeah, if the green light's on, you're good.
Okay. The cognitive vacation thing. Sorry.
Well, we want to get you, Larry. Sit over a seat. We want to get you.
Does that work?
Yeah, I think.
Oh, yeah.
Does it work, Mike? Yes.
Okay. With regard to the cognitive vacation, some people never go off vacation. And I want to point to 3 people I've had the great pleasure of working with who are regarded to be really creative, smart people. They came from three different areas. One is Max Fugere, who's the chief engineer at NASA. Max passed away 2 years ago. He was my partner, he was my close friend. And brilliant guy. And people would say if I were in a room with 100 people and Max disagreed with the 99 others, I'd always go with Max. Max had an insatiable curiosity about everything around him. There was nothing he missed. We went on a Goodyear blimp ride one time. We had a company together, Space Industries, and took a day off and went on the blimp. Within 15 minutes, he was flying the blimp, and he was just one of these guys that he absorbed everything around him. Another is Fred Singer, who I've had the close opportunity to work with. He's a climate guy. The top climate scientist, I think, in the world. In fact, he visited my home. He just left yesterday. Fred's the same way. He's interested in everything. He picks up languages. There's nothing he doesn't observe. It's remarkable. His mind is always tuned into what's around him. Another is Burt Rutan. I'm going to have the great privilege of staying with him this summer. We're going out to visit his new home. Bert's, we know Bert as a great aircraft designer, spacecraft designer. Bert's also a big climate guy, like I am. Very interested in climate dynamics. And he's done a lot of work on it. So here's a guy who designs spacecraft. He's interested in climate dynamics. So what I notice about people that I really admire is that they're just always aware of what's around them. And I think so much of creativity comes from analogs. It's what we see something wiggling around out here, and other people don't make that connection. And I think what really creative people do is they see analogies. They see systems, and they say, well, gee, look at the way these ants are operating here, and they're building architectures, or and I think the really creative people are not the people that get out of the box. They're people that aren't in a box. and everything, they realize that engineering, language, mathematics are tools. They're the tools we use. They're the ways we discipline ideas, the way we communicate, the way we organize concepts, the way we draw relationships between two things. They're our toolbox. We need to be familiar with those tools. And the more tools we have, language, foreign languages are becoming increasingly important. Understanding, interest in how things work, how people work, how people's minds work, how people work when you put them together in a little box together in a spacecraft. So I'd like to just sort of add that to this notion of the cognitive vacation, is that I think we give short shrift to the times we think are idle, or we think we're daydreaming. We're not. We're working.
Yeah.
Our minds are working, and we're absorbing things. We're discovering things. And so much of what we call intuition, we kind of dismiss it. Well, we can't quantify intuition. Well, intuition is a sum total of all our experiences. It's all the stuff that's wiggling around out there that we draw upon that says, well, gee, that doesn't look right. Why doesn't it look right? Because our experience has said there's an anomaly here, or there's a relationship here, or I don't like the way this person looks at me because I'm reading body language, or I'm looking at this set of tables, and I'm looking at this curve, and it looks contrived. It doesn't work. Michael Mann comes to mind here. Pennsylvania State guys. But I think it's absorbing all these things, and it's giving full appreciation to the dimension of our just assimilation of things that are around us, and being tuned into them, being aware of them, and giving them every bit as much importance as every other tool in the box.
That's right. Absolutely. Absolutely. That's fantastic.
I'm going to echo that one thing. One of the professors I had as an undergrad, and this will be short, his comment was simply, be a curious observer. Be a curious observer. And I think those of us that are engineers, we're afflicted with this phenomenon of always wondering how something works. Like you walk through a door and you look at the doorknob and you're like, how does that work? Be that curious observer. So very important.
The other thing I want to say, and I'm going to talk about it in the next half of this, is I like to seed my team with people who are just, like Larry said, I'm going to use that term from now on, we're never in a box. And what the Zen call the beginner's mind. I'm going to introduce you to my good friend Don Pettit, who's up in orbit right now. And I brought him into this problem not just because he was this creative genius or he was a genius and could build anything you could possibly think of. But if you ever watch Don Pettit when he's in orbit, you watch his lectures, you listen to him, he approaches everything like a child, a beginner's mind. He's an expert in one area, but like Larry said, he wants to absorb everything around him, and he approaches it just like a child. He's wondered by it, he's mystified by it, it gives him intense excitement, and allows him to try things and test things and fail, just like children. And that's when we were pretty happy.